This is a video going over the Algebra 1B semester exam review for Unit 4, Topic 1. On the exam, you'll be given a formula sheet that looks just like this, so don't forget about that and don't spend your time worrying about the equations that are on this since they will be given to you. For items 8 through 10, classify each function below as linear, exponential, or quadratic, and justify your answers. So remember, when we're looking at these, we can see that our x's go up by 1, so we don't need to worry about the x's. What we're going to focus in on is how our y's change. For number 8, what we can see is that our y's go up by 3 every time. One way to figure this out is to do 11 minus 8, 8 minus 5, 5 minus 2, and see if you get the same number every time. In this case, you do. You get positive 3, and that indicates to us that the function is linear. Our reason behind this, there's two ways to put it. We can say the first differences are constant. We can also say that they're the same. Our first differences are constant, or we can also say there is a constant rate of change of 3. Either way, these are explanations that justify your answer. So there's a constant rate of change of positive 3. This indicates to us that we have a linear function, and if we graphed these points, they'd be in a straight line. Question number 9, if we look at it, we can see that it's not going to be linear. This is going up by 3, this is going up by 5, and this is going up by 7. But when we look at our second differences, we can see 3 plus 2 is 5, 5 plus 2 is 7. This tells us that our function is quadratic. So it's quadratic because the first differences are linear. This means that our first differences, which are these right here, have a constant rate of change of 2. Another way we can say this is, so the first differences are linear, or the second differences are constant. Either of these explanations will justify your answer, and no, you do not need to put both. Finally, for the last one, we can see that it's going up by 2, then 4, then 8. And when we see a repetition like that, we've got to look to see if we're actually multiplying. And we are. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Another way I can look at it is 16 divided by 8, 8 divided by 4, 4 divided by 2. If I get the same number every time, then I know it's going to be exponential. So, an exponential function is defined by there being a common ratio of 2. Each y value increases by a factor of 2. Meaning it is multiplied by 2 every time. Another way you can say this is that there is a common ratio of 2. All right, question number 11. Question number 11 says a rectangle has a length that is 6 inches longer than its width. Well, in these cases, I always love to draw a picture. So we have our length and we have our width, and the length is 6 inches longer than the width. So whatever my width is, I'm going to be adding 6 to it. So let's say, let W equal the width. Let the length equal W plus 6. Therefore, we want to write an expression for the area of the rectangle. Well, area is length times width. So we're going to multiply our length, which is W plus 6, times our width, which is W. Another way we can write this is W times W plus 6. Another acceptable answer would be to multiply that out and get W squared plus 6W, but this is unnecessary. We have a similar problem with number 12. A rectangle has a length that is 4 inches shorter than its width. Well, if my width is W, my length is going to be 4 inches shorter than the width. So whatever my width is, I'm going to take away 4 inches. So again, let W equal the width. Let length be W minus 4. Area is going to be length times width. So we want our length, which is W minus 4, times our width, which is W. Another way to write this is W times W minus 4, or if you multiply it out, W squared minus 4W. Any of these answers would be acceptable. Please note, though, that both of these say an expression, so your final answer should not have an equal sign in it. For items 13 through 15, a function of time is given. In each item, determine the average rate of change on the given interval. Give the units for your answer. Well, if you remember from when we learned this, average rate of change is very similar to finding the slope. If you think about it, D equals RT is going to be our distance equals rate times time. We want to solve for R, the rate, so we divide both sides by T, and R is going to be equal to D over T. But we want this over an interval of time. So we need to incorporate that by finding the difference between our two different times in our interval in order to get the speed. So for number 13, we're given a table and we want the average speed on the interval 2 is less than or equal to t, which is less than or equal to 5. To find that rate, we're going to be doing d of 5 minus d of 2. Meaning I want the total distance traveled between my distance at time 2 to my distance at time 5. And if you remember, let's say this is 0, we have 2, and we have 5. My distance traveled in 5, take away my distance traveled to 2, leaves us with this distance between 2 and 5. And that's why we subtract. Same thing goes for the time. I'm going to want the time of 5 minus the time of 2. So d of 5, I'm going to look at my table. I see at 5 seconds, the person was at 125 feet. And at time 2, the person was at 20 feet. Time of 5 is 5 seconds minus 2 seconds. Now notice, if you hear what I'm saying, 125 feet, 20 feet. Feet is in our numerator, and in our denominator, we have 5 seconds minus 2 seconds, which means we have feet per second. Well, 125 minus 20 is 105. 5 minus 2 is 3. And dividing that out, that gives us 35. Well, when we put our units in there, we have feet per second. So what we really have is 35 feet per second. And that's how fast the person was traveling. For number 14, we're going to do something similar. We're looking over the interval of 1 is less than or equal to t, which is less than or equal to 6. So to find that rate, I'm going to need my bacteria. I'll just use B to abbreviate. Bacteria at time 6 minus bacteria, B, not 6, bacteria at time 1, divided by my time at 6 seconds minus my time at 1 second. Well, my bacteria at 6 seconds is right here. This is the point 640. So my bacteria is going to be 40. At 1 second, I'm at 1.5. So 40 minus 5 bacteria over 6 minus 1 seconds. Well, again, I'm going to jump down to the units really quick. My bacteria is on top, so number of bacteria, it's in my numerator, divided by my time in hours. 40 minus 5 is 35, 6 minus 1 is 5, and together that equals 7. So really what I have is 7 bacteria per hour. And these are the units you should use. So a little bit of simplified than what I wrote here. Bacteria per hour. Question number 15 gives us a function. It gives us d of t equals 500t plus t squared. Well, we are looking for the average speed on the interval. 0 is less than or equal to t, which is less than or equal to 4. So it still is the same thing. My rate is going to be d of 4 minus minus d of 0 over t of 4 minus t of 0. Problem is that we don't have a table and we don't have a graph, so we don't know what these numbers are. Well, we actually know t of 4 is going to be 4 seconds and t of 0 is going to be 0 seconds. But we don't know what the d of 4 and d of 0 is. We need to calculate it. So if I have this function right here, I want to know what is d going to be when the time is 4. So I'm going to plug that in, and I'm going to have 500 times 4 plus 4 squared. Well, 500 times 4 is 2,000. 4 squared is 16. So I'm going to get 2,000 plus 16, which is 2,016. And it says right here, d of t is in kilometers, so 2,016 kilometers. I also need to do that for d of 0. So 500 times 0 plus 0 squared is 0 plus 0, which equals 0 kilometers. So when I go back to here, d of 4 is going to be 2,016 kilometers minus 0 kilometers. So again, my units are going to be kilometers on top because that's my distance over time in minutes. Well, 2016 minus 0 is 2016. 4 minus 0 is 4, so divide by 4, and we get 504. This means that we're going to have 504 kilometers per minute. Ooh, that is hard to read, sorry. Give myself some more space. Kilometers per minute. And there's your average speed on that interval. All right, the number of weeds on a lawn can be written as the function w of d equals 25 plus 60, where d represents the number of days since spring started. Part A wants to know, is the rate of change of this function constant? Explain your answer. Well, if we look at this function right here, we see that it fits into the scenario of y equals mx plus b, which means that it is a linear function. This is a hint right here to tell us that the rate of change of this function is constant because linear functions have a constant rate of change. So as written, the rate of change of this function is constant because the function is linear. Linear functions have a constant rate of change. This would be a thorough and excellent explanation to justify your answer. So the next question is, what is the rate of change? Well, the rate of change is our slope. So our rate of change is going to be m in our equation of 25d plus 60, meaning that our rate of change is 25. Finally, what are the units for the rate of change? Well, remember that rate of change, I'm just going to abbreviate it, rate of change, ROC, is going to be our change of y over our change of x. Well, we know that we're going to have 25 over 1, but what is our y? Well, our y is w of d, which means that it's the number of weeds. So 25 weeds over our x. Our x is going to be d, which is number of days, so 1 day. Therefore, our units are going to be weeds per day. Question 17. Jack is inventing a variation on bowling. Here are the first 4 rows of pins. In the first row, there are 2 pins. In the second row, we can see that we've added 3 pins for a total of 5 pins. Then we added 5 pins for a total of 10 pins. And then we had the same scenario for 4 rows, but now we've added 7 more pins for 17. Let P of R represent the total number of pins in R rows. Complete the table based on the total number of pins. Well, in 1 row we have 2, 2 rows we have a total of 5, 3 rows we have a total of 10, 4 rows we have a total of 17. We can see that with the pictures. What we also notice is that we're adding 3, and then we're adding 5, and then we're adding 7. So naturally, our next one we'd be adding 9. 17 plus 9 is 26. 3, 5, 7 plus 9, now we're going to do plus 11. 26 plus 11 is 37, and there's our table. What we can also see from this is that we've got plus 2, so this must be plus 2, plus 2. We have a quadratic function, and that is actually our next question. What type of function is represented by the table above? Well, quadratic function is represented. And to explain why you chose that type of function, I'm going to focus on my second differences being constant, or the fact that my first differences have a constant rate of change, meaning they're linear. So the first differences are linear, or you can write the second differences are constant. Next, it asks you to write a function for P of R. Well, there's 2 ways we can write this. We can write it recursively, or we can write it explicitly. I will do both for you, but it just asks for one. The recursive rule, you always have to start with your first one. In this case, P of 1, which equals 2. Then we're looking at what P of R is by continuing the pattern. This is a quadratic function, so it's a little bit more challenging. We always have our previous term, so P of R minus 1. Then we have to figure out what we're adding to the previous term every time. So in this case, every time we're adding the next odd number up. The best way to figure this out is to use whatever your second difference is, in this case 2, and multiply it by r. So I know that I'm going to be adding 2r. So let's take an example. I've got p of r, and I'll even write it up here. P of r, so let's say p of 2. My previous term, p of r minus 1, is going to be 2. And I'm going to do plus 2 times r. Well, 2 times r is 2 times 2, which is 4. So I'm going to do 2 plus 4, which is 6. Hopefully you're following along with this. But what I actually need p of 2 to equal is 5. So how do I go from 6 to 5? Subtract 1. So I'm going to take my p of r minus 1, and I'm going to add to it whatever my common difference is, 2 times r, and I'm going to take away 1. Let's double check to see if this works. Let's take p of 5, for instance. P of 5 needs to equal 26. Well, p of 5 is my previous term, which is 17, plus 2 times 5 minus 1. Well, 2 times 5 is 10, minus 1. 17 plus 10 is 27, minus 1 is 26. And it works. The explicit function, you can try to look at the table. In this case, it's a fairly easy one to figure out, or you can use your calculator. If I look at the table, I know that it's going to be how do I deal with my r to get it to my p of r. I always don't like looking at the first one because those can be a little tricky. We know it's going to be quadratic, so at some point in time, r is going to be squared. Well, 2 squared is 4, but I need it to be 5. So maybe r squared plus 1. 3 squared is 9, but I need it to be 10. There's that plus 1 again. 4 squared is 16, plus 1 is 17. So my explicit rule is going to be p of r equals r squared plus 1. Now, if you can't figure that out from the table, you can always use your calculator. So you'll go to second, stat, and enter your x's into list 1. Oh, I'm sorry. You're going to do second, stat, and then you're going to edit. And your x's are going to go into list 1. Your y's are going to go into list 2. We know this is quadratic, so then we can do stat, arrow over to calc, and then when you do that, you're going to find, in this case, number 5, which is quad reg. If you put your data into list 1, your x's into list 1 and your y's into list 2, all you then need to do is press enter, and it will give you your a, b, and c for your quadratic function of y equals ax squared plus bx plus c. And what you should see is that it gives you this. Finally, part E, Jack decides that he will have 12 rows of pins. What is the total number of pins that he will need? Well, one way you can do this is to extend the table. You know, if 6 is 37 and we just added 11, we're then going to add 13 to get our 7. 37 plus 13 is 50. To get my 8, I'm going to be adding 15. 50 plus 15 is 65. To get my 9, I'm going to be adding 17. 65 plus 17 is 82. To get my 10, I'm going to be adding 19. 82 plus 19 is 101. To get my 11, I'm going to be adding 21. 101 plus 21 is 122. And to get my 12, I will then add 23. And 122 plus 23 is 145. Another way we can do it is to use the explicit rule. Well, if P of R equals R squared plus 1, and R is the number of rows, I'm actually looking for P of 12, which means R squared is actually going to be 12 squared plus 1. Well, 12 squared is 144 plus 1, which is going to give me 145. Either way you do it, you'll get 145 pins in the end. Question 18. Look at the pattern of dots below. So we have figure 1, which has 3 dots, figure 2, which has 8 dots, figure 3, which has 15 dots, if you count them, and figure 4, which has 24 dots. Let d of n be a function that represents the number of dots in figure number n. So part A wants us to complete the table below. Well, figure 1 has 3 dots, figure 2 has 8 dots, figure 3, from counting, has 15 dots, and figure 4 has 24 dots. Well, to go from 3 to 8, I add 5. 8 to 15, I add 7. 15 to 24, I've added 9. Well, continuing the pattern, 5, 7, 9, I'm next going to be adding 11, and 24 plus 11 is 35. And then I'm going to be adding 13, and 35 plus 13 is 48. My next question is, which type of function, linear, quadratic, or exponential, is represented by d of n? Well, what I can see is that I'm adding 2, adding 2, adding 2, adding 2, adding 2. So, the function is quadratic, and this time we have to give a reason. So the function is quadratic because the first differences, so that's what's in blue and green, the first differences are linear, meaning those values have a constant rate of change of 2, or we can say that the second differences are constant. So the function is quadratic because the first differences are linear or the second differences are constant. So next it asks us to write the function rule for d of n. Again, we can write this either recursively or explicitly. So again, the recursive rule, you first need to state your very first term. So in this case, d of 1 equals 3. The rest of the recursive is going to be written by me figuring out what am I doing to the previous term to get to the next term. So my next term is d of n. My previous term is d of n minus 1. So what am I adding or subtracting, but in this case adding because it's getting larger, what am I adding to d of n to get my next term? Well, as I said with question 17, you're always going to multiply your variable, in this case n, by that second difference. So I know it's going to be of some form, like 2n. Now I'm just going to look, I'm going to do an example to see what happens. So let's say I was doing d of 3. Well, I'm going to take my previous term, which is 8, and I'm going to add something to get, my goal is to get 15. So 8 plus what is 15? Well, I know that I'm going to be doing 2 times n. 2 times n is 3, so that's 6. So 8 plus 6 plus what, or minus, plus or minus what, is going to give me 15. Well, 8 plus 6 is 14, so I know that if I add 1, I'll get 15. So I'm going to try 2n plus 1. I want to check to make sure it works for others, just to know that I'm right. So let's try d of 6. d of 6 is my previous term, d of n minus 1, so 35, plus 2 times 6 plus 1. So this is 35 plus 2 times 6, which is 12, plus 1. 35 plus 12 is 47 plus 1, which is 48. And that is what I want, so this works. To do my explicit one, I've got to look at the table again. I'm going to see that I know it's going to be quadratic, so I'm probably going to be doing d of n equals n squared of some sort. But this one's a little harder to figure out. So let's look at d of 2. 2 squared is 4, but I've got to go to 8. So 4 plus what for 2 gives me 8. For 3 squared is 9. 9 plus what gives me 15. For 4 squared is 16. 16 plus what is going to give me 24. Well, in this case, 4 plus 4 is 8. 9 plus 6 is 15. 16 plus 8 is 24. How can I relate what's in blue to the value of n that I'm using? Well, 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. So maybe I'm going to be adding 2 times n. Again, though, you can use your calculator. I wouldn't even spend the time trying to figure this out unless it was really obvious. Another answer you might have gotten, though, is d of n equals n times n plus 2. This is absolutely another option, another way of looking at it. So whether you figure it out from the table or you figure it out from your calculator, you should have gotten one of these answers. Finally, for part D, how many dots will be in figure 9 show how you determined your answer. Well, you can do it in one of two ways. You can continue the table. So if I had 5 was 35, 6 was 48, and I want to figure out 7, 8, and 9. To go from 5 to 6, I added 13. So this time I'd add 15. 48 plus 15 is 63. Then I'd add 17. 63 plus 17 is 80. And then I'd add 19. And 80 plus 19 is 99. Another way to do it is to use my explicit rule. If I know d of n equals n squared plus 2n, I want to know what d of 9 is. So that means 9 squared plus 2 times 9. 9 squared is 81. 2 times 9 is 18. And 81 plus 18 is 99. Either way you do it, there will be 99 dots in figure 9. And that is the end of Unit 4, Topic 1 of this review.